Hi, I have here a Hall effect sensor. It's a Honeywell SS49E, which is a pretty common run-of-the-mill Hall effect sensor. And you can see that it's not very big. That's a normal finger sitting there. You can see how thin it is. It's about 1.6 millimeters thick. And there's actually more than just a Hall effect sensor inside this package. There's also an amplifier. And if you look at it, it's got 3 pins here. The leftmost pin, if I can get my pointing device in there, come on, there we go. So the leftmost pin here is your power supply pin, VCC. The middle pin is ground, and the right hand pin is the output voltage. Now VCC can vary between about 2.7 to 6.5 volts. It's normally 5 volts. That's a good voltage to use. So you put 5 volts between the left hand pin and the center pin, the power supply pin and the ground pin, and you measure the Hall effect voltage out of the right hand pin between that pin and ground. And with no magnetic field, the output pin will be sitting at about half of what the VCC is. So if you're running at 5 volts, the output will be sitting around 2.5 volts with no magnetic field. If you put a magnet such that the north pole is on the back side of the sensor, the output voltage will increase above the 2.5 voltage proportional to the strength of the magnetic field. If you put the north pole on this surface, the voltage will go the other way, it'll decrease. And the rate at which it varies is linear in this device, and it's about 1.4 millivolts per Gauss, and Gauss is just the measure of the strength of the magnetic field. In this video I'm going to show you how to use this device, this Hall effect sensor, to measure the RPM of the shaft of a motor. And I'm going to stick a magnet onto the shaft of the motor. It'll spin around and pass by this Hall effect sensor, producing a pulse every revolution. And then I'll take the output of this sensor to a microcontroller and use it to trigger a timer and measure the time between pulses. So you get 1 pulse for every revolution, and you can measure that time between pulses. Then you can figure out how fast the shaft is turning around and convert it to revolutions per minute. Connected the sensor up to 5 volts, and the multimeter is reading the output voltage. And as you can see, there's no magnetic field on the sensor right now, so the output voltage is reading 2.5 volts approximately. Now if I take a magnet, and there's a magnet stuck on the end of this pen here, and I bring it closer to the sensor, you can see the voltage is changing and it's dropping. So that probably means, that the south pole of this magnet is touching the back of the Hall effect sensor. If I were to put the magnet on the other face like this, you'll see how the voltage is increasing. Now I've taken a magnet and I've taped it to the shaft of a motor, this one here, and spin it around. You can see there's the magnet taped to the motor, and I'll hold the spinning shaft close to the Hall effect sensor. In fact, I'll just turn it here so that the sensor gets the full strength of the magnetic field. You see how it drops down. So when the magnet is close to the sensor, oops, in the right position, you can see the voltage drops, and when the magnet's on the other side away, it doesn't really have that much effect. It goes up a little bit. So what I'm looking for is a negative going pulse every time the magnet on this motor comes around near to the Hall effect sensor. So I've got the motor running here, and I'll bring it close to the sensor, and you'll be able to see on the scope a signal there. And I take it away and the signal goes away. Now as you can see on the scope, that signal isn't very big. It doesn't go down to ground, and I want it to pulse between some high voltage greater than 3 volts, and it's only going to 2.5 volts, and it doesn't go to ground. So I think I'm going to need to put an amplifier in the circuit here. This is the amplifier circuit that I'm going to use. This is the Hall effect sensor right here, and the 3 pins on it, the VCC pin, the ground, and the output pin. And this is just an ordinary op amp, an LM358. It's a dual op amp. I haven't shown the second op amp. I've just for the second op amp I've just shorted the two pins, the input pins here, to ground, and that way it doesn't make any noise. And I'm only using this one op amp here. Now this circuit does two things for me. And the first thing is it adds some gain to this signal, to this negative excursion. I want it to go right to ground, and as you saw on the oscilloscope, it didn't go that low. And so by adding some gain, I can make that signal go to ground. I also want to be able to bias that 2.5 volts bias. I want to raise it to as high as I can. I want it higher than 2.5 volts so that the microcontroller can see it as a high when the signal, when there's no magnetic field there, when there's no negative pulse. And that's what this resistor does here, this variable resistor. It allows me to adjust the offset. The op amp is designed so that the output pin here can actually go to the negative rail here. In this case, I've put the negative rail on ground and the positive rail on 5 volts. This op amp will not is not able to bring its output pin right up to the 5 volt rail. In fact, it's guaranteed to be about 3.5 volts instead of 5, which is still high enough voltage to tell the microcontroller that it's a logic high. When I hooked this thing up and I measured it, it actually went to 4 volts, and which was a surprise, but a very pleasant surprise. It was useful that way. So with this amplifier in the circuit here, I was able to turn those very tiny little blips that you saw initially on the oscilloscope, those little blips like that, and actually made them, well, if you draw a little picture here, what we saw on the scope initially was something like this. So there's the voltage level where there was no magnetic field, and then when the magnet passed by the Hall effect sensor, you got a little pulse like that, and then it pulsed again when the magnet came around again. And this was at about 2.5 volts. Now, a microcontroller is not going to see this as a pulse. It needs to see this signal get right down to ground here. So by adding this op amp circuit here, I was able to shift this 2.5 volt level up to about 4 volts. And when the magnet came by, I'll show you on the scope here, but the signal actually went right down to ground and then back up again. Something underneath this is causing me to draw improperly here. And back up. And so that's a good signal. The microcontroller can see that falling edge and trigger an interrupt or something that's easily detected by the microcontroller. So here's the amplifier circuit I built. Let's just zoom in a little bit here so we can see the components of it. This is the op amp, and then these wires here simply short the two inputs of the unused amplifier in this package to ground. The used amplifier is on this side, pins 1, 2, and 3. And this white lead here is the output. This is the potentiometer that I use to vary the offset. Over here is the Hall effect sensor. Okay, let's have a look at the amplified signal now on the oscilloscope as I bring the motor close to the Hall effect sensor and then move it away. Now let's capture that signal on the scope and do some measurements. Tricky getting the motor in the right spot without grinding away on stuff. That's pretty good. Turn the cursors on, and good. Let's look at the falling edge here. Actually, let's move this over a bit. I'll measure that point there and that point there, and I'm reading 67.6 milliseconds between those 2 points. Scope's already calculated that it's 14 Hertz, which means 14 revolutions per second. And if I were to multiply 14.8 by 60, that gives me 888 revolutions per minute. Now keep that RPM measurement of 888 in mind, because we're going to come back to that later. But now I want to talk about a couple of things I had to consider before I started writing the software for creating a tachometer. The first thing I had to do was determine how was I going to detect this low going pulse here. Now I could tie the output of this Hall effect sensor directly to an I/O pin and just simply monitor the I/O pin constantly until it read 0, which would be down here, and do what I needed to do and continue from there. But the problem is that that state will exist for as long as this pin is low here. And as you saw in the oscilloscope pictures, it stays low for quite a long time in terms of microprocessor time, because you can do a lot in this little bit of time here, which is only a few milliseconds. So what I really needed to do was to be able to detect this edge, and then it would create an event in the microcontroller, set a flag or something like that, and then I could do what I needed to do and clear that flag, and that event would not be triggered again until the next falling edge over here. But if I was looking at the level, I could do all of my calculations down in here and then try to clear that event, and it would immediately be set again because this pin is still low. And the only way I could do that was to tie this output to the external interrupt pin int 0 on the ATmega, which is what pin is it here? It's pin 4, number 4 on the chip itself, which is port D pin 2. And it's an interrupt pin, and it can generate an interrupt, and it can be set up to generate an interrupt on a falling edge, on a rising edge, or when it's low. Or also I think when it's high too. I'll have to look at the manual again. But anyways, I decided to set it up so that it would create the interrupt event on this falling edge. And what that does is it simply sets a flag, and you have to initialize the interrupt system in the microcontroller for it actually to generate an interrupt. And if you don't want to use an interrupt, you can just monitor that flag. It's a easily readable flag. It's just a bit in a register, and you can monitor that, and when it goes high, that indicates that this edge has been detected. And then you simply clear that bit by writing a 1 to that bit position, and it clears it. And so I could clear it here, and it's never going to get set again until the next falling edge. So that's what I decided to do. I tied this output of the op amp here to external interrupt pin interrupt 0, int 0. And then I configured the int 0 interrupt to trigger on a falling edge, and if you look through the datasheet for the ATmega, it describes clearly how to do that. Maybe I can quickly go through that later. And then so now I have the option of actually generating an interrupt where the microprocessor gets interrupted and goes through an interrupt vector and into an interrupt service routine to do what I need to do on each of these edges. Or I could just simply sit there in software polling that flag, and when the flag becomes set, then I can do something. And that's actually how I wrote it in this quick example of software that I'm going to show you. So that's how I got about the first problem here, is just how to reliably detect this falling edge here. The next issue I had to determine was how to time the time between these pulses. Now that time varies quite a bit depending on how fast the shaft of the motor is spinning. And if I wanted to measure something upwards to 10,000 RPM or more, we're looking at less than 3 milliseconds in between these two interrupts, or these two edges. Or if I wanted to measure something down to just a few RPM, that could be many multiples of milliseconds between these two. So I needed a counter that had enough resolution in order to accumulate that time. So I chose timer 1 because it's 16-bit counter. The other two timers, timer 0 and timer 2, are 8-bit timers. Now this timer is actually pretty complicated, as are all the timers. There's many features that you can enable on it, including a bunch of different ways of doing PWM. But I'm not interested in PWM. I simply want to time. And so I set the timer up in its simplest mode, which is actually the default mode when it resets, which is simply an incrementing timer. So every tick it gets from whatever clock source, and I'll describe that in a minute, it increments by 1, and it'll just keep incrementing, and then when it reaches the maximum 16-bit count, which is in hexadecimal FF, it'll simply roll over to 0, 0 and start counting up again. This can actually generate an interrupt as well when this rolls over to 0, which will be useful too, and I'll show you why I might want to use that. So anyways, I'll explain how timer 1 is set up, and the clock source for it. I want it to be continually clocked. I do want to turn it on and off, and there's reasons for that, and I'll show you in a bit. But I'll have it run from the internal oscillator, from the main oscillator of the microcontroller. In my case, it's a 20 megahertz crystal that I'm using on my proto board here. The Arduino boards use the 16 megahertz crystal. But that really doesn't make a huge difference, except in the amount of time it can actually time. So but at 20 megahertz, this timer would increment pretty fast. It would probably, if you started the timer here, it would increment to the overflow state to about here, and I want to be able to count all of this time. So I don't need it to go that fast. But the timer can be driven from a prescaler, which divides the main oscillator by several different values, but the maximum amount of division it will do is by an 1024, and so I chose that tap. And so I divide my 20 megahertz. So if I divide the 20 megahertz by 1024, that gives me a tick every, what did I work out, 51.2 microseconds. So every 51.2 microseconds this timer will increment, and that way I start the timer here on this falling edge, and then I detect the next falling edge, I stop the timer and I read it, and then I know how many times it's clicked over when I get to this point, and I multiply that by 512 microseconds, and it gives me the amount of time in between these two edges here. And since this is one revolution of the shaft, it makes it really easy to figure out what the RPM is from that point, and I'll show you how to do that in a minute. So that's how I set up the timer as well. Now, what I could have done here was, between each edge here, I could have done everything. I could have started the timer at 0, accumulated the time here, cleared the timer, started it again, did all the calculations, and output the data to the liquid crystal display. But I felt that because the liquid crystal display takes so long to update, that at higher RPMs I was not going to be able to get everything done in this time here. And so I decided to do it a slightly different way. And what I do is, on the first edge, I start the timer at 0. It accumulates, and I do nothing else in here. On the next edge, I stop the timer. I record that value. I clear it, and then I do all my calculations and output the data to the display. And I wait for the next falling edge, and then I start the timer again and do this all over again. So every second edge, it outputs a new RPM value to the display, which for all intents and purposes is plenty fast enough for most applications. And again, you'll see that in the code. Now, before I get into the software and have a quick look at the some data sheets here, And this is the datasheet for the Tachometer 328, which is the microprocessor and microcontroller that's used in the Arduino, and it's also the one that I'm using here. And let's have a look at the pin configurations. This is the 28-pin dual inline package that's used on the Arduino Uno, and it's also the same one I'm using here. And the output of the Hall effect sensor I've connected to this pin here, which as you can see is the int0 pin, which is the fourth pin, pin 4 on the package, and it's port D2 pin. And if I go to the Uno, this is the Arduino Uno, and I look for port D2, which is here, and follow it out to there, it's Arduino pin number 2. So if you're using an Arduino, that's the pin that you can use for this application. Let's go back to the Tachometer. Now I want to look at the external interrupts. So if I scroll down, I don't have to, we can go here, external interrupts. And you can just read through this on your own. It just describes the two int0 and int1 pins, and also the PC int pins. And most of the I/O pins, other than these two, int0 and int1, are the PC int pins. And they are interrupt on change. So what that means is if the logic level on that pin changes from whatever it is to a new logic level from 0 to 1 or 1 to 0, it will trigger the interrupt. But I'm not looking for that because I don't want it to be interrupting on the rising edge of the signal as well. So I just want to I want to have more flexibility. So I look at the int0 and int1 pins, and if you just scroll down here, we don't need to look at that. All right. These are the registers that you have to write to set up the pins. And this is the external interrupt control register for the two different int0 and int1 pins. And what they use is these two bits for the int1 pin, and these two bits here for the int0 pin. And these are the tables here that you look at, and they happen to be the same. Both pins work the same way. So in my case, I'm using interrupt 0, and I set it up to the falling edge of int0 generates the interrupt request. So you can set it up to be a low level or logic change, just like the other pins, the other interrupt pins, or the rising edge as well as the falling edge. So I want to put 1 0 into the last two bits here of this register. So EICRA equals 1 0 or 2. You can put 2 in there. You'll see it in the software as well. So that sets up the sense for that pin, for the interrupt 0 pin. And if we scroll a bit further down, we look at the interrupt mask. Now if you want this pin to generate an interrupt, you've got to set this bit here. This represents the mask for bit, or for the int0 pin, and this is for the int1 pin. And you need to set this pin to 1, or this register bit to 1, and that enables the interrupt as long as the global interrupts are enabled. And I'm not using interrupts in my application here, so this register, it doesn't really matter. But if you do want to use the interrupts, then you need to set this bit to 1, and then set the global interrupt bit as well. And there are instructions in C code that you could use to do that. Let's see, one is it's called SEI, and the other one is called CEI, and that just means set interrupt enable or clear interrupt enable. And that's the to turn on the global interrupt so that all interrupts will work. And then once you do that, this interrupt will work as well. But I'm not using the interrupt, but I do want to use the interrupt flag register. And what happens is when the int0 pin detects the falling edge, as I've set it up to, it will set this bit here in this register to 1. and that flag will be set regardless of whether the interrupts are enabled or not, or whether I'm actually using the interrupts or not. This flag will get set. And this is what I'm looking at in my software, is this flag to become set. Once it's set, I know that the interrupt has occurred, or the conditions have occurred, and then I can do what I need to do. To clear this interrupt, and you must clear it, it doesn't do it automatically, you just write a 1 to this bit here as well, and that will clear it. So that's a quick look at the interrupt pin here. Let's look at quickly at the timer here. Now this has this timer, as well as the other two timers in this microcontroller, have an incredible number of features. They can all do PWM, and they can do various other things as well. What I just want to use timer 1 for is a simple counter. I want it to increment with every tick. So looking through all this, like I said, there's a great deal of information here. You know, you can go through this and read it and start playing with it. And then you can figure out what you want to do with this timer. I've gone through all this, so I have a pretty good understanding how these timers actually work. But I read through all this trying to figure out what to do with them. And there's a lot of information here, but you can just wade through it to get to what you want. And I'm going to go right down to the register description. And there's two important registers that you need to use with this timer. One of them is called TCCR-A, and the other one is TCCR-B, and the one in here means just timer 1. And this is the timer counter control register A. And these bits here set the mode for the output pin A, and this sets the mode for the output pin B. We're not using those output pins. This is how you set up the PWM. The WGM bits here, this sets up how the timer is actually going to operate. Let's get down to there. Here we go. So these two bits are in this register. This bit here, these two other bits are in timer control register B, which I'll get to in a second here. But what I want to do is set this up as just a normal counter. I don't want any of this PWM stuff, which is all the rest of this here. And so I just need to put zeros into this register here. So if I go back up to it, TCCR1A is going to just have all zeros in it. And this diagram here represents what the initial value is here, right here. This is what this register will take on when the microcontroller is reset. And it happens to be the situation that I want. But I still will write zeros into this just to make sure it's going to work. The other register that I'm going to look at here is the control register B. I don't need to worry about these two bits. I'm not using an input capture. These two here are the other two bits that determine the mode of the timer, and they're going to be set to 0. It's these three bits here that I'm interested in, which stands for the clock select. And we go down to here. So these three bits select which clock source. And it comes up in the reset state with these three bits 0. It means no clock source is selected, therefore the clock is not running. It's not going to increment. And that's the state that I'll use when I stop the clock. But I want to select the prescaler of 1024, and so I write a 101 in this register in these last three bits here. I ignore these upper ones. They can all stay 0. So I write 0 into these three, that turns the clock off. I write 101 into these three, that turns the clock on with a 1024 prescaler. And that's all you need to know about how to set up the register. There's a third control register. We don't have to worry about it as well. It resets into the situation where you're not using this one anyways. And then the actual count that we're going to read is 2 bytes. It's a 16-bit counter. You are able to read each of these bytes independently, or in the software you just call it TCNT1. And again, I'll show you in the software. and that accesses it as a 16-bit register, and you just treat it as a 16-bit number, and it makes the software a little bit easier to write. Configuring the interrupt pin here. So it's on data port D, and it's pin 2 on that port, so I must set it up to be an input pin, and that's what the data direction register, and wherever a 0 appears in that register, that pin will become an input. So this tilde symbol means just invert this this symbol here, which is 2. So I've made the input, or that pin, into an input, which is the interrupt 0 pin. I go to the interrupt enable register, and I set this bit here in it, and that tells the system to generate an interrupt on the falling edge of the pin. Looking at the timer 1, timer control register A, I just set it to 0, which is the reset value, but I just made sure it's there. Sometimes if you have to reset it in the middle instead of a power-up reset, I just want to make sure that this actually ends up in the simplest state, which is an incrementing timer. And then I created these two macros back here. Timer off, which is all zeros into that control register, and then timer 1 on. We put this 101 code into the register, which connects up the 1024 tap of the timer, or of the prescaler for the timer. And then the timer control counter, which is the actual register that increments, I just cleared it, made it 0. And right now the timer is off. I go into the forever loop here in the main routine. What I'm doing here is simply looking at the interrupt flag for the interrupt pin 0, and I'm waiting for it to become 1. So this statement here is, while this pin is equal to 0, which is true, it's just going to stay in this while loop, which is we're doing nothing here. We're just wasting processor time. When the interrupt occurs, when that falling edge is detected, this pin will be set to 1. The state will no longer be true, and it'll fall through. So now, as I showed you in the hand drawing in the previous clip here, I simply turn on the timer. This little bit of code here just simply resets the prescaler so it starts at 0 as well, and everything is synchronized nicely. Remember, the prescaler will accumulate 1024 counts from the main oscillator before it ticks timer 1. And so that can create a little bit of an error in the RPM calculation. So I just simply start everything at 0, including the prescaler. And then this statement here is I simply clear the interrupt flag that we detected here by simply writing 1 to that flag in that register. Then I go into this next wait loop here, which is the same as the previous one here. We're just sitting here wasting time waiting for that interrupt flag to be set, which is on the next falling edge from the Hall effect sensor. So what I do once I detect that edge is I turn the timer 1 off. I take a copy of the accumulated count, and then I clear it. And here's where I do my calculations. Now, tachometer is the value that I'm going to output to my liquid crystal display. It is the value of the shaft speed in RPM. I've got another macro here, which I'll show you how I defined it, and it's used to convert the count that was accumulated by timer 1 into RPM. The next thing I do is I take this value that I just calculated in RPM, and I convert it to a string, an ASCII string that gets displayed on a screen. And this is a function called long to ASCII. It's a built-in function, and it's in this library called standardlib, stdlib.h. So you have to include that to get this function to work. It's a really simple function. It takes the long, this variable here. It does its calculations. This is a the address of a string, which is just an array of characters, which I defined up here, and I said it's 10 characters long. And what it does is it converts this long to A, L to A, converts tachometer into a string, and it stores it in a string here. And this number here, 10, is just use base 10 as the conversion factor. So I can convert it into binary, I can convert it into octal, I can convert it into hexadecimal. If I wanted to convert it into hexadecimal, I would change this to 16. If I wanted to convert this into binary, I would change this to 2. But since I want to use a decimal number that we all know and understand, I just put in the value of 10. This function here is in the library that I wrote for a liquid crystal display, and I include that up here. And I forgot to mention, but you have to initialize the display. I'll talk about that in a bit. Actually, I've gone through this in a previous video, so maybe I won't talk about it too much right now. But down here, I simply clear the first line, because that's where I'm going to write it. Remember, this is a very simple function, or it's a very simple program. All I'm going to do is continuously write the value of tachometer to the first line of the display. So I need to clear that, because as tachometer changes in value, the length of the string will change. And if the new string is shorter than the previously written string, then what will happen is parts of the end of the previous string will still remain on the display when you write in the new string, and it gets confusing. You have all these extra digits that aren't part of the new number. So I just clear the whole line and write it fresh each time. And this function here, put string, just writes out the string that's stored in ooh, what happened there? Let's clear that up. There we go. There we go. Mistyped something here. Made a mess of my program. So anyways, this function here just simply takes what's in temp string and writes it to the display. And here I clear the interrupt flag, and this is the end of the while loop, the main while forever. And it goes back here waiting for the next falling edge. And it just does this repeatedly over and over and over and over again. Now, going back to how to convert the count that's accumulated in timer 1 to RPM. It's actually quite simple. So I said there was 551.2 microseconds per count. So we just take the timer count, multiply it by 551.2 microseconds. So that gives you the total number of microseconds in this time between the two edges. And then if I invert that, divide it into 1, that will give me the revolutions in revolutions per second. And if I want to get that into RPM, I simply multiply this by 60. So if I take the number 60 over timer 1 count times 51.2 microseconds per count, I get this in RPM. Now, I don't need to throw these numbers into my software. I can do a couple of tricks here outside of the software, so I don't have to run through this calculation every time I use it in the software, and it saves a lot of computing time. I do the calculations out here and just give it a number. So if I take microseconds and I put it on the top here, I get 60 times 10 to the 6th out here is the conversion to microseconds, but I want to keep all the digits here. So if I were to write this number as 512, it would be times 10 to the minus 7. So I just put in another 10 here. So I've got this number, and then I divide by 512. And when I do the calculations, I come up with a number which is quite large. I've written it down somewhere, but I forgot where I put it, so I'm just going to go through the calculations again. And I get a number that is quite large. It's 11,718,750. That's a pretty big number, but the computer can handle that. So what I'll do is this number becomes a constant that I put into my code. And when we look at the software, I'll show you how that number actually doesn't actually appear. These numbers do. I put in my software something that looks like this: 60 times 10, 1, 2, 3, 4, 5, 6, and then divided by 512. And I create a macro using this, and I'll show you again in the software how that works. I could just put this number in there, but for clarity in the software, when somebody's reading my software, excuse me, it makes more sense to do this. So looking back at the software again, I'll show you how this constant timer to tac comes from, which is, if you remember my hand scribbling there on the paper, I had 60 times 10 million divided by 512. And I could have put that number 11,718,750 in there as well, which would do the same thing. But I let the compiler do this calculation. When the compiler runs through all of this, it simply does that calculation prior to creating any code that gets burned into the microcontroller. This is just for documentation purposes. And down here, I use that factor, that macro, and divide it by the accumulated ticks of the timer between negative going pulses from the Hall effect sensor. So this is a very, very quick piece of software that I've written here. Probably not the best way to do it. In fact, there's a lot of time wasted because it's sitting here doing nothing while waiting for a falling edge from the Hall effect sensor. A better way to do this would be to put this into an interrupt service routine, and that way in this while loop here you could be doing other things. For example, if this was part of a control system to control the speed of a motor, one input to that motor would be, or that control system would be, the speed of which the shaft is turning, and the microcontroller could do the calculations to figure out an error signal to feed back to the motor control system to be able to speed up or slow down the motor so that it sits at the right RPM. So anyways, this is, like I said, very, very simple demonstration software to show you how to implement a tachometer with a microcontroller. Let's have a look at what it actually does when it's running. Okay, let's have a look at this thing in actual operation here. My motor just stalled. Let's try it again. There we go. So here's the display, and I'll hold the motor up to the Hall effect sensor, and there we go. 890. It's bouncing around quite a bit, but remember when I did the calculations on the oscilloscope, I got about 888. So this isn't far off from what I calculated or measured on the scope. So there you have it. Here is a very simple demonstration of using a Hall effect sensor to measure the shaft speed of a motor. Before I go any further, let's play around with this a bit. I'm going to crank up the motor a bit, and I'm having unreliable connection problems here with my power supply. Let's crank it up a bit. So there's the motor going at about its maximum speed, just over 3,000 RPM. When I move too far away from the sensor, it just freezes up. There's many improvements that can be made to this software, but this is, like I said, a very quick and simple demonstration of using a Hall effect sensor to create a tachometer. So I hope you guys enjoyed this video, and if you have any questions, just put them in the comments on YouTube. I go back and read them periodically, and yeah, hope you enjoyed it. Go to YouTube and give me a thumbs up, and keep watching. I've got another video coming up shortly. So thanks for watching. I'll see you the next time. Bye for now.